Okay, Unit 4 is going to be our trigonometry unit, and so to start with, we are going to talk about this first slide here talks about degrees, minutes, seconds versus decimal degrees. So we've got to be able to convert back and forth. So just for a second though, I just kind of want to talk about what is degrees, minutes, and seconds versus decimal degrees. So decimal degrees is when you actually write it as a decimal, like 32.5768, whatever, and then you just put a degree symbol. And then degrees, minutes, and seconds would be something like 32 degrees, 8 minutes, and 53 seconds. I'm just making that up. Okay, so the 1 slash represents minutes, 2 slashes represents seconds. So basically what's happening there with the 32 degrees, 8 minutes, and 53 seconds is they're taking, and this is how we convert back and forth and we learn how to do that. They're taking a degree. So let's pretend this is a degree. Let's blow it up really big. And this is 1 degree. Oops, I didn't mean to write a 10 here. Let me try that again. So here's our big angle. This is 1 degree. This angle is 1 degree. Okay, what minutes means is that you take this 1 degree and then you start slicing it into little pieces. So it's really hard to draw, but you would have 60 pieces in that 1 degree. That's what it's talking about, 60 pieces in that 1 degree. And then seconds takes one of those minutes, so one of those minutes, and then it does it again, slices it into 60 parts, kind of like our clock system, hours, minutes, seconds. It kind of works that same way. So it's just a more accurate way of measuring an angle in degrees, minutes, and seconds. We typically work with decimal degrees, but probably in the industry of aeronautics, I bet they would be going with degrees, minutes, and seconds more than decimal degrees. Space, all that kind of stuff. I feel like that anytime you're talking about angle and you want it to be a little bit more exact, they're going to go with degrees, minutes, and seconds. So how do we do that? Well, so this first example right here has 37.425 degrees, and we want to convert that to degrees, minutes, and seconds. So that's what the DMS stands for. So first of all, take this part right here, the 37 degrees is good. We know 37 is our unit part. That's our degree part. It's this piece right here that we need to put into minutes and seconds. So we're going to take that decimal, 0.425, and we're going to multiply it by 60 minutes over 1, basically 1 degree. So those of you that have done unit analysis, that degree symbol and that degree symbol will reduce, and then you're going to multiply that out. So you're going to go 0.425 times 60, and you're going to get 25.5. So what that tells us then is this piece right here, the 25, is our minute piece. So right now we've got 37 degrees, and now we figured out the minute piece. And now we take the rest of the decimal, this piece right here, the 0.5, and we multiply it by 60 again. So we take 0.5, and we end up with 30. So that's our second part. Okay, so 37 degrees, 25 minutes, and 30 seconds. That's what 37.425 degrees is equivalent to in degrees, minutes, and seconds. Okay, now your calculators have this button, and we'll kind of talk about that in a minute. I'm just showing you how to do this longhand just so that you'll know. So now what we're going to do to convert the other way, so let's say I give you 42 degrees, 24 minutes, and 36 seconds, and I want to do that as a decimal degree. Well, the 42 pieces, okay, the 42 degrees is fine. You leave that alone. You take your minute and divide it by 60. So the minute part divides by 60, and the second part divides by 3600. Now remember, the reason you divide it by 3600 instead of 60 is because you have each of those seconds is 60 minutes per the second, right? So you got to do 60 times 60. Did I say that right? Anyway, you have to do 60 times 60. So you have to take the 36 and divide it by 3600. So then you could just go ahead and figure that out as a decimal. So you'd say 42 point and then plus 24 divided by 60 plus 36 divided by 3600, and you get 42.41 degrees. So that's decimal degrees. Okay, so that one's decimal degrees. Okay, so let's pull up calculators and see if we can figure out where these buttons are and how to use them on our calculator. Okay, so here's my TI graphing calculator. So what you're looking for is the angle menu. So the angle menu is right above the app, so I'd hit second and then the apps button. And see how you have a degree symbol. So right there is the degree symbol on top. Then you have a minute symbol. And then down below on number 4, you have this converted to degrees, minutes, and seconds. So that one, we can actually use our calculator with just one button. So if we wanted to take our 37.425 degrees and convert it, so let's go ahead and go back to our main screen. Let's type in 37.425. Okay, now I'm going to go back to that menu and I'm going to convert that to degrees, minutes, and seconds, and I'm going to hit enter. Okay, and there we go, 37 degrees, 25 minutes, and 30 seconds. So if your calculator has that button, great. I don't care if you use that. If you have to convert it by hand, you know how to convert it by hand if your calculator doesn't do that. The little TI-30XS buttons will also convert. So if you have that non-graphing calculator, there is an angle button on that calculator also. So you just have to scroll down and find the correct menu for that one. So both these two calculators, which are the two common ones that we use here at this school, will do that converting. Okay, now let's look at the other direction. How do we go the other direction? So let me slide this over here so we can see our problem. Okay, so we're going to convert 42 degrees, 24 minutes, and 36 seconds to decimal degrees. So once again, it's pretty easy to do it by hand. Divide by 60, divide by 3600. If you want to do it on your calculator, this one might be faster to do by hand versus by the time you find all the buttons to type it in. But anyway, how you would do that is you'd say 42, and then we'll go back to the angle menu. And we're going to have to use that degree symbol, so I'm going to hit enter. And then 24, back to that angle menu, and now I'm going to go down to minutes and hit enter. Now on the graphing calculator, unfortunately, the 36 seconds is not in this same menu. It's not here under that same menu. To find that seconds, you have to look above, I think it's above the plus sign. So, and it's green, so you're going to have to go, let me get my thing back over here. We're going to go alpha and then the plus sign. There we go, and there's our second symbol, and then hit enter. And there you go, 42.41 degrees. Okay, so you can convert it by hand or you can use your calculator. So in this unit, we're going to start taking our degrees and we're going to be looking at a more exact form, either more decimal places or we're going to convert them to degrees, minutes, and seconds. The one thing you got to make sure that when you're doing your problems, keep them all in one type of unit system. Don't do some of them in degrees, minutes, seconds, and some of them in decimal degrees. Do them all the same, okay? They would all want to be the same. All right. This slide right here is a quick review of what is a radian. So not only can you measure angles in degrees, but we can measure them in radians. So a radian is a pretty big measurement. Degrees are really small. A radian is pretty big. And what you do, how they calculated a radian is they took from the center, it doesn't matter what the size of your circle is, You measure the radius, however long it is, and then you take that length and you lay it around the circumference of the circle. Okay? And then whatever that unit is, so from here to here, this is considered 1 radian. So 1 radian is a pretty big measurement. In a circle, there would be, how many radians do you think would be in a circle if you had to guess? Hopefully some of you are guessing 6.28 radians. And in some of my other classes, if you've been in some of my other classes, we actually do this exercise where we actually mark them all off. So I give you a piece of string and we actually go around and mark off, and then you find out that yes, indeed, you can only get, all the way around, you get 6, and then you have a little bit left for your 2/8. Okay, so so you don't get exactly 6 pie pieces, because if you got 6 pie pieces, um, then you would have, uh, what am I trying to say here? Never mind, forget that. Um, Backtrack. So one radian is a huge, big number. In degrees, it's about 57 degrees. Okay, that's what I was trying to say. That if you had only 6 pieces around, then it would be 60 degrees, each of those. And 1 radian is just a little bit less than 60, so you have to have a little piece left over. And if you look at the 6.28 radians, hopefully that's kind of ringing a bell to a very common number, 2 pi. So if you were to measure around a circle in degrees, a circle exactly is 360 degrees. In radians, the circle is 2 pi. Those are both exact measurements. So what we're going to do is we're going to use that idea to convert back and forth between radians and degrees. So if 360, let's backtrack to this one right here. So if 360 degrees is a full circle, then 180 degrees must be a half a circle. And if 2 pi is a full circle, then pi would have to be a half a circle. Those are equivalent measurements right there. And that's the key that we're going to use, because that's the simplified one. You could do 360 and 2 pi, but we'll do the smaller number. That's what we're going to use to convert back and forth. You guys are most comfortable working with degrees because that's what we normally work with, but radians is another type of measurement that you should be able to work with. So right here, I've got 150 degrees, and we're supposed to convert that to radians. So remember, your key is 180 degrees is the same thing as pi radians. So if I want to convert, then I'm going to have to multiply by 1. And I'm going to have to use 180 and pi. So you have to figure out how to put that ratio in so that it will reduce. Well, if I've got degrees in the numerator, I need to have degrees in the denominator so that this degree symbol will reduce with that degree symbol. And now you have 150 pi over 180. And basically, you could do this all in one step. You want to reduce those fractions. So they're both divisible by 10, and it looks like they're both divisible by 3, so that would be 5 pi over 6. So this is 5 pi over 6 radians. Now, we don't write the word radians out there like that. It's understood to be just 5 pi radians, 5 pi over 6 radians. Okay, so now we want to convert 75 degrees 30 minutes to radians. So before we do that, we want it to be in decimal degrees before we convert it. So we're either going to have to get our calculator out. So remember, we're going to convert 75 degrees 30 minutes to decimal degrees. Well, the minutes, if I want to convert it, is the one where we just divide it by 60. So this is the same thing as 75.5 degrees. 30 over 60 is 0.5. Okay, so we're going to take 75.5 degrees and we're going to multiply that by pi over 180. We want the degree symbols to reduce. And so now we're going to have 75.5 pi over 180. And typically you don't want to leave 75.5. You don't want to leave that as a decimal. So let's just go ahead and see what, and a lot of times we'll leave it in terms of pi radians and not all the way out. Um, so this one right here, if we wanted to get rid of this decimal, we could multiply both the top and the bottom by 2. We could double it, and we would end up with 151 pi over 360. So that would be considered pi radians. Now, if you wanted to work it all the way out as a decimal, this is an exact answer, 151 pi over 360 radians. But if we wanted an approximate, we could say 151 times pi, and I usually just hit the pi button that's on the calculator, and then divide that by 360, and you'll get about 1.3177 radians. Okay? And if we don't put any units behind it, then we understand it to be radians. If you put a degree symbol, you don't write the word radians. If you put a degree symbol here, then I know it's degrees. So in this chapter, guys, if you're talking about degrees and you get lazy and you don't put the degree symbol, it's going to be wrong. From here on out, when we're working with our trig stuff, if you want your angle measure to be degrees, then you have to write the degree symbol. You can't be lazy. You have to write it. That's the only way to tell the difference between degrees and radians. All right, so here on the right-hand side, we're supposed to convert these to degrees. So 3 pi over 4 radians, that's in pi radians. So if I'm going to convert that, once again, my ratio is 180 degrees and pi. I've got to figure out which way to put them in. Well, since I've got a pi in the numerator and I usually just think of it this way, guys. If you're going to degrees and you want degrees, the degrees needs to go in the numerator. End of story. If that's what you're looking for, degrees needs to go in the numerator, and then these will reduce, your pi's will reduce, and you end up with, let's see, I think 4 will go into 180 also. So 45. So this is 3 times 45, which is 135 degrees. Okay, so down here on this one on the bottom, 1.3 radians, there is no degree symbol. So when I go to convert it, I'm converting to degrees, so I'm going to put the 180 pi on 180 degrees on top and the pi on the bottom. Okay, so 1.3 times 180 is 234 over pi degrees. This one we would probably keep going. This is an exact answer, but I think we'd take 234 and divide that by pi and get about 74.4845 degrees. Okay, so we've got to be able to work with degrees as well as radians, and in our degrees we now know that we can break those down into degrees, minutes, and seconds. Okay, now these angle measures, we're going to just start graphing them and putting them in quadrants and working with them. So just a couple of vocabulary words. When you're drawing an angle, you're always going to have an initial side, and then you do some kind of a rotation to the terminal side. Okay, and then this point right here is your vertex. So initial side, terminal side. Okay, in standard position, the initial side is always the positive x-axis. Okay, so in standard position, your initial side is always right here. This is your initial side. And your vertex is always at the origin also. And the vertex is at the origin. Okay, so when you go to graph things, so if I go, when I graph an angle, so I start in standard position, So let's say I start right here. Here's my vertex. Here's my initial side. If I rotate counterclockwise, so I rotated counterclockwise. When I go to put that degree measure in, that's considered a positive angle degree. Okay, that's a positive, that's an angle measure is a positive degree. Counterclockwise rotations are positive. If you take that initial side, so let's say I start here, this is my initial side now, and I rotate clockwise, so let's say right there, and I want to put that degree measure. Well, if I rotate clockwise, that's going to be a negative. So let's say that's a negative 100 degrees. So depending upon whether your angle measure is positive or negative, that tells you which way you rotated from the positive x-axis. So we all have to start from the positive x-axis, otherwise we'd end up in different places in the coordinate plane. So that's our standard. Initial side is always the positive x-axis. Okay, so this says graph all of these in standard position. So you could just make quick sketches of these. So 60 degrees, that would be, you're going to start right here. So 60 degrees would rotate in a positive direction. And so this is 60 degrees. 195. So 195 would be a little bit past 180, so I'm just guessing right here. So that's 195. Okay, 270 would be on the y-axis. That's 270. And negative 240, you would start here, rotate. This is a negative 180, so a negative 240 would put me here. So that'd be a negative 240. Okay, that looks pretty sloppy. So now I'm going to erase all of that so we can see what we're going to do next. So those are all just when you just started in your positive x-axis, rotated clockwise or counterclockwise. But what happens if you have to go more than one rotation? So this one right here, 400 degrees. Well, this is how you show that. Here's my initial side. So I show that I go all the way around the circle. That's 360. And then I go another 40 degrees, and that's considered 400 degrees. That rotation is 400 degrees. So when I look at this and I see this spiral, I will know, since I have one complete spiral all the way around, I've got 360 plus a little bit, this little bit right here, okay? And then the same thing if you go negative 720. So negative 720, I would start right here, positive x-axis, rotate clockwise. So negative 720 would be, this would be negative 360. Go all the way around again, and I would stop right here. That would be negative 720. So that's two complete rotations all the way around. Started on the positive x-axis and it ended on the positive x-axis. Okay, so that's how we graph in standard position when we're graphing our angles. We're always going to start with the positive x-axis, and we're either going to rotate counterclockwise or clockwise. Okay, so coterminal, this says find two angles, one positive and one negative, that is coterminal with the given angles. So coterminal, we're going to use the word coterminal. That means we're going to try to find angles that all have the same terminal side. So remember back here on this slide, when we talked about initial, this is where we start, initial side, and then we rotate and we stop, that's considered the terminal side. So we're going to try to figure out angles that get us to that same terminal side but can have different measurements. So for this one says negative 150. So if I start right here, here's my initial side. Negative 150 would mean I would rotate clockwise to about right, oops, too far, to about right here. This would be a negative 150, okay? So if I wanted another angle that's coterminal with one that's positive, keeping track, this is the terminal side right here. We need to figure out another measurement that gets me to that side. Well, what if we go the other direction? Let's start right here and rotate to here. What would that degree measure be? Well, we know that all the way around a circle is 360, right? So if I went negative 150 in one direction, then I must have to go positive 210 in the other direction. So this must be a positive 210. Okay, and now I need to come up with another negative angle. Well, the only way to do that is you have to start right here on your positive x-axis. You're going to rotate all the way around. So that would be negative 360, and then I'd have to add a negative 150 to that. And so I'd end up at a negative 510. Now, we could do this for infinity, guys. There's infinite number of coterminal angles. All we have to do is just go around our axes, you know, around and around and around more as multiple times. One time, two times, three times, four times, it doesn't matter. Okay, let's try it again. So this time, 75 degrees. So here's my initial side, and 75 degrees will probably put me, I don't know, something like that. That's a positive 75 degrees. So now remember, we want to end up on the same terminal side. So we want to end up right here. But I want to rotate the other direction. So that means I want to go negative how many degrees? Well, 360 minus 75 is 285. So this is a negative 285. And then if I want another positive coterminal, then I'm going to go around 360 plus 75. That's the minimum one. And we have 435. Okay, so basically what was I doing with those two, negative 150 and 75, when I was trying to figure out coterminal angles? Basically, I'm either adding or subtracting 360 degrees. That's basically what we did. We added or subtracted 360. If you take a negative 150 and you add 360, that gives you 210. If you take a negative 150 and you subtract 360, it gives you a negative 510. So when you're trying to find coterminal angles, you're basically adding and subtracting 360 degrees to figure out what they are. Okay, now the bottom two are in radians. So what we want to do is we don't want to have to convert back and forth. I know that you guys are really comfortable with degrees, and you could convert 3 pi to degrees, and you could make that work. But I want us to be able to work with radians the way it is and not have to convert back and forth. So in order to do that, we kind of have to get a feel for what our axes are going to be in terms of radians. So 0 would be right here, and pi would be right here, because that's a half a circle if we were counting 180. And then 360 would be right here, which is 2 pi. Okay, so I know that much. So then that must mean if I'm from 0 to pi, then from here would be pi over 2. And then I've got to figure out this right here is about 3 pi over 2. Okay, so that kind of gives us an idea of where we're going to put them. So this first one, if it says 3 pi, so if I wanted to do 3 pi, and that's positive rotation, I would start here. Here would be 2 pi, and then 3 pi would put me right there. Okay, so I want an angle that is coterminal with that. So I could just rotate this direction right here, and that would put me on the same terminal side. Because remember, my terminal side happens to be right here. This is where I ended. This is my terminal side. Okay, so one of our answers could be negative pi. And then how could I get another positive answer? Well, I could just go, instead of going all the way around, I could just start here and go here, and that's a positive 180. So I could say, oh, I forgot to put my negative sign on this one. This was negative pi, and this one could be positive pi. Okay. Now, you don't have to have pictures to do this. We could do the same thing that we did up there at the top. If we want to find one positive and one negative, we could take 3 pi and add and subtract, but this time instead of doing 360, we would do 2 pi, whatever its equivalent is. So notice, if you take 3 pi and you add 2 pi, that gives you 5 pi. That wasn't one of the ones that we picked, but that is a correct one. We could count that one. But let's go the other direction. If I go 3 pi minus 2 pi, that gives me pi. It didn't give me the negative one, but if I do it again, if I take the pi and I subtract 2 pi, you end up with the negative pi. So if you're adding and subtracting 2 pi, you can do that as many times as you want until you get a positive or a negative. Okay, so like I said, there's multiple answers. All right, so this last one, we got to figure out where to put 2 pi over 3. What quadrant do we think 2 pi over 3 is in? So I've kind of got this basic pi over 2, pi, 3 pi over 2. I'm pretty sure that 2 pi over 3 is less than pi. But would that be in the first quadrant or the second quadrant? Well, if you thought about this in terms of, let's erase these now, since these were all just in halves. And since my fraction is 2 pi over 3, so let's think of this in thirds. This is 3 pi over 3, right? That's the same thing as pi. And then this would be 0, and this would be 6 pi over 3. If we want them to be in thirds, well, if we take 3 pi over 3 and we cut it in half, then, well, we don't even need to cut it in half. This is 3 pi over 3. We want 2 pi over 3. So we're not quite there. So our answer is going to be right here in this spot right here somewhere. It's going to be in this quadrant, second quadrant. Okay, so let's find a coterminal. So we could rotate this way, all the way to here. Remember, so this would be 2 pi over 3, so this one's going to be negative. So once again, you could subtract, if you wanted, 2 pi, and you could get that answer. Well, get a common denominator, so that would be 6 pi over 3. So that would be a negative 4 pi over 3. So this is a negative 4 pi over 3. And then if you want to get another one that's positive, just take the 2 pi over 3, this 2 pi over 3, and add 2 pi to it, and that'll get you in the same spot. So we're going to add 2 pi. So common denominator, once again, is 6 over 3, and you end up with 8 pi over 3. So those are equivalent coterminal angles with 2 pi over 3. So like I said, if we can get to where we can do those in terms of radians without converting, that's what we want to be able to do. Okay, so here we want to find the complementary and supplementary angles of the given angles. So remember, complement, in case we've forgotten, are two angles that add, so two angles that add to 90 degrees, or in terms of radian, 90 degrees is pi over 2. And then what is the supplement of an angle? So supplementary angles are two angles that add to 180 degrees or pi, okay, in terms of radians. So if things are complementary, then they add to 90. If they're supplementary, they add to 180. So if I'm going to try to find the complement of 2 pi over 5, then I'm trying to find the other part of that angle that makes it add up to 90 degrees. So we want it to add to pi over 2. So if I want to find its other part, we want it to add to 90, then we're going to go ahead and subtract that from pi over 2. Okay, so pi over 2, if I'm going to find if I'm going to find the complement of this one, 2 pi over 5, I'm going to take pi over 2, and I'm going to subtract 2 pi over 5. Okay, so we need a common denominator, which is going to be 10. So this is going to be 5 pi over 10 minus 4 pi over 10. So the answer turns out to be pi over 10. So its complement is pi over 10. So the complement of this one is pi over 10. Okay, if we take 4 pi over 5 and we try to do the same thing with this one, so I'm going to start with pi over 9, or excuse me, pi over 2, that's 90, and I'm going to subtract the given angle, 4 pi over 5. So if I get a common denominator, that's going to be 10 again, so that's going to be 5 pi over 10 minus 8 pi over 10. And notice you get a negative 3 pi over 10. Okay, that's not making sense because the supplement should be or complement should be a positive number. The reason we ended up with a negative number here, guys, is because 4 pi over 5 is actually bigger than 90 degrees to begin with, or bigger than pi over 2 to begin with. I mean, it's almost pi. It's almost 180 degrees. So this one doesn't have a complement. So this one is no complement for this one. This one's a none. Okay, no complement on that one. If your angle's already greater than 90 degrees, then you don't have a complement. Okay, now the bottom one, we're trying to do the supplement. So remember, supplement is 180 or pi. So I'm going to say pi minus 2 pi over 5. Well, common denominator is going to be 5. So it's going to be 5 over 5. So 5 pi over 5 minus 2 pi over 5 is 3 pi over 5. So that's the supplement of 2 pi over 5. And over here, if I've got 4 pi over 5, same thing. I'm going to start with pi because that's 180, and I'm looking for its supplement. So I'm going to subtract what they gave me, 4 pi over 5. Common denominator. And we end up with this one right here turns out to be pi over 5. Okay. So pi over 5 is the supplement of this one, and 3 pi over 5 is the supplement of that one. So pretty much, unless your given angle, so once again, if your given angle is greater than 180 degrees, it won't have a supplement either. So the original angles, guys, if you're looking for complement, it has to be less than 90 or pi over 2, and supplement has to be less than 180 degrees or pi to find those complements and supplements. Okay, and then the last two things here are some formulas that you're going to need to know how to do. We've got arc length, and the last one is area of a sector. So this lesson today has a lot of little tidbits of information in it that we're going to kind of pull together as we go through the chapter. But to start with, we're just kind of learning lots of little individual ideas. So this one right here is arc length. So this is given to you in terms of radians, this formula. Arc length, remember guys, is if you're talking about a circle, so here's a circle, and you're trying to find the arc length of something, what's happening is, doesn't matter what your angle is, so maybe let's make this my angle. If you're looking, actually let me draw that circle different so you can see what I'm talking about. I'm going to do a different angle. So here's my circle, and I'm going to do this. Okay. And if you're talking about arc length, you're talking about the outside of the circle right here. So if you were to look at that, you would say that that arc length is 1/4 of the circumference, right? It's 1/4 of the circumference. So right now what I have is 1/4 of the circumference, and the circumference of a circle is 2 pi r. That's easy to see because of the angle I picked. Okay, well, how that works out in formula-wise for any angles is this piece right here. It's always going to be 2 pi r, okay? But the fractional part out in front is going to be whatever the angle measure is you're talking about. So let's say I made my arc length a little bit longer and I went over to here, okay? So now I'm going to say that that angle measure is 135 degrees and I need that full arc length. Well, now it's 135 degrees of the 360. All the way around a circle is 360, and it's still times by the circumference, 2 pi r. It's always going to multiply by the circumference, guys, if you're talking about arc length. So how do we get this formula over here where it says S equals R times theta? So in degrees, basically what we're saying from that picture over there is that your arc length, and this, you may have done this formula earlier in some previous classes, I don't know. It's whatever the angle is that you rotate over 360 degrees times the circumference times 2 pi r. Okay, so over here in this original problem, when we could look at it and tell that it was 1/4, that was because it was 90 degrees out of 360. The second problem I did was 135 out of 360. So how do they come up with this formula in terms of radians? Well, basically they take this formula that we used before in degrees and they convert it. So instead of doing 360 degrees, what's 360 equivalent to in radians? It's 2 pi. So how do they get this formula? It's arc length equals theta. So instead of writing 360, they write 2 pi, because this is going to be in radians now, times 2 pi r. And look what happens. The radians, 2 pi and 2 pi drop out, and you're left with theta times r. So that's why in this formula, this center angle, if you're going to use S equals r times theta, and I have no idea why they use the letter S for arc length. Okay, I don't know the answer to that. But if you're going to use that formula, then theta, this theta has to be in radians. You can't use degrees. If you want to do degrees, you have to do this formula over here. Okay, so here we go. It says find the perimeter of 60-degree slice of a large 7-inch radius pizza. So if we're going to find a piece, so here's my pizza, and here's my piece of pizza. It's 60 degrees. I want the perimeter of that piece of pizza. This is 7 inches right here. I need to know this plus that. So I need to find the arc length. Now, if you wanted to, I'll do it both ways. So it's given to me in degrees, and I know the formula for degrees, so I think I'm just going to use the formula they give me. So I'm going to say that's 60 over 360 times 2 pi, and what's my radius? 7, 2 pi r. Okay, so this turns out to be 1/6 times 14 pi. Okay, so let's go ahead and figure that out as a decimal. So 14 pi divided by 6 is about 7.33, and that kind of makes sense to me because, I mean, 60, 60, 60 would be equilateral, right? And all the sides would be 7. But since this is on the curve over here, we know it's probably going to be a little bit bigger than 7. So the radius or the arc length is 7.33 inches. So that means my perimeter is 21.33 inches. Okay, that's using the angle that they gave me. But now let's use S equals R times theta, because a lot of kids just like to use that because for some reason that formula just sticks in their head, R times theta. It's easy to remember, it's easy to use. Theta angle has to be in radians, so I would take 60 and convert that to radians, so that would be pi over 180. And if you do that, you end up with pi over 3. So I would just take that and I would say, okay, my radius is 7, times it by pi over 3. Okay, let's see what we get. 7 times pi divided by 3, and we get the same answer, 7.33. So they both work, and whichever one you want to use is fine. They're both going to work. You just have to know that S equals R times theta has to be in radians to use that formula. Otherwise, you have to do the other formula. Okay, so the other one is the area of the circle, and it's the same idea as the arc length. So if you have a circle and you wanted to know the area, so let's say I'm going to do the 90 again, and I want to know what this area is of my circle that's shaded, you would say it's 1/4 of the circle that's shaded. Well, what's the area of a circle? It's pi r squared. Can you read that? That's pretty. Let me rewrite that. Okay. So it's the same idea. So I could make that anything I want as long as my central angle is at a 360, and whatever that gives me whatever portion of the circle is shaded, and I times it by the area of a circle formula. Okay. So in degrees, that's the area of a sector formula. The area of the sector is going to be theta over 360 degrees times pi r squared, the area of a circle. Now, if we want to do this in terms of radians, we do the same thing we did before. Instead of using 360, we do 2 pi. So we get theta over 2 pi times pi r squared. So the pi's reduce, and you end up with theta r squared over 2. And so how do they write that formula? Instead of doing it r squared over 2, they just do 1/2 r squared theta. So they write that as 1/2 r squared theta. So that's the area of your sector formula. So one you can use if they give this, but you have to remember if you're going to use this formula, because this looks a little cleaner maybe to remember, this has to be in radians. Has to be in radians. Otherwise, you have to use this formula down here. Okay, this question says a sprinkler on a golf course fairway sprays water over a distance of 70 feet and rotates through an angle of 120 degrees. Find the area of the fairway watered by the sprinkler. Okay, so let's put the sprinkler right here. And it sprays a distance of 70 degrees, so or 70 feet, so that's kind of its radius right there. And it sprays 120 degrees. So we'll say that's 120 degrees, okay? That's how it sprays. So we can use it the way it's set up because I know that I can say, okay, the area that it's spraying is 120 degrees out of 360 times pi r squared. 70, not 7. Let's change that to a 70. Okay. So this area turns out to be what? Let's just go ahead and figure that out. 120 divided by 360. And I'm going to times that by pi and r squared. So I get 5,131.27 feet squared. Okay, but let's just say we didn't want to do that formula. We were like, well, I'd rather just use this formula where it's 1/2 r squared theta. So it's going to be 1/2 70 squared, and then I just have to put theta in. Well, theta has to be in radians. So you have 120 degrees, and you need to convert that to radians before you can use that formula. So 6 goes in there, 2, 6 goes in 3. So this is 2 pi over 3. Okay, so let's see what we get when we do that. Hopefully we get the same answer. So 70 squared times 2 times pi divided by 6. And we get 5,131.27 feet squared. Same answer. So it doesn't matter if you go with degree formula or radian formula. I feel like in the book, they really want you to use the radians. That's kind of the new idea when we were working in pre-calc. They mostly work with radians and not degrees. It's whatever you're most comfortable with, but I feel like the book is going to focus more on the radian formulas, but you have both here. Okay, we're done.